Then I will expand binomial, and then you collect like term and do all the simple algebra. Now that is one application of the Moivre's theorem, expansion of cos raised to power n and sin raised to power n. So the next one is more or less like this, but there is a slight difference. So application 2. Let me circle this. So application 2 of the Moivre's theorem is the expansion of cos n theta, like cos n theta, product of cos, and sin n theta. The previous one is cos raised to power n, sin raised to power n. This one is cos n theta and sin n theta. Okay, so how do we use this one? How do we expand cos n theta and sin n theta? We know that if z is equals to cos theta plus I sin theta, and then z bar, z raised to power minus 1, that's cos theta minus I sin theta. If let's say I take the square of both sides, if I take the square of both sides, z squared now from the first one, z squared will be what? Cos theta plus I sin theta all squared, which is cos 2 theta plus I sin 2 theta. That's z squared, right? If I take the square of this, say this is equation star, and the second one is star star, for example. So if z is this, z squared is cos theta plus I sin theta all squared, and z, that's cos 2 theta plus I sin 2 theta. Now, what this thing means is that, okay, if I continue, if I generalize Zn, so Zn will be cos n theta plus I sin n theta, if n is positive, I sin n theta. So if I want to expand, wait, so if I want to expand, let's say I want to expand cos 5 theta. You know, from here now, z squared is cos 2 theta plus I sin 2 theta. Going back to our elementary, this is the real part, and this I sin 2 theta is the imaginary part. Why? Because of this I. Zn, cos n theta is the real part, and I sin n theta is the imaginary part. So what this thing tell me is that, suppose I want to get the expansion of cos 5 theta. What do I need? Cos 5 theta is just like having z5. You know, z5 is cos theta plus I sin theta all raised to power 5, like this. So z5 simply means the real part of cos theta plus I sin theta all raised to power 5. Again, if I need cos 5 theta, for example. So going by idea of z5, z raised to power 5 is cos theta plus I sin theta all raised to power 5. You know, according to the Moivre's theorem, if I have cos theta plus I sin theta with any power, that power will multiply it like this. So this is just like the real part of the expansion of cos theta plus I sin theta raised to power 5. So let's take for example. So let's expand. Let's get the expansion of find the expansion of sin raised to power sin 5 theta, not sin raised to power 5 theta, sin 5 theta. So we know that sine is what? Sine is the imaginary part, abi? So sine is the imaginary part. So I'll just say sin 5 theta is the imaginary part of the expansion of cos theta plus I sin theta all raised to power 5. So it's the imaginary part of the expansion of cos theta plus I sin theta raised to power 5. So what I will now do is that I will go and expand cos theta plus I sin theta raised to power 5. So we then expand cos theta plus I sine theta all raised to power 5. Then we take the imaginary part. So the imaginary parts are the parts with I, the parts carrying I. Now to make my work easy, so this is what I want to expand. I will just say that let cos theta, let's call it A, and let's call sine theta, let's call it B. It means we need the expansion of A plus IB, A plus IB all raised to power 5, right? So if I go by the idea of binomial expansion, if I have A plus IB raised to power 5, this one will first carry the highest power and this IB will carry the lowest power 0, plus this A will carry power 4 and this is IB raised to power 1, plus A raised to power 3, IB raised to power 2, plus A raised to power 2, IB raised to power 3, plus A raised to power 1, IB raised to power 4, and plus IB all raised to power 5. So anything raised to power 0 is 1. So A plus IB all raised to power 5 is equals to A raised to power 5 is A raised to power 5. A raised to power 4 is A raised to power 4. I raised to power 1 is I. B1 is B. So this will be A for IB. A raised to power 3 is A raised to power 3. Now, I squared from our iota, I squared is what? Is minus 1. So that minus will change this one to minus. So I B squared. A raised to power 2 is A raised to power 2. I raised to power 3. I raised to power 3 is I square I. That's minus I. So this is minus A square IB cube. AIB 4. I raised to power 4 is 1. So that's I squared squared. So that's 1. So this one will be plus A B raised to power 4. IB all raised to power 5. So what is I raised to power 5? I raised to power 5 is I. So this is plus IB5. And after you expand, you put the coefficient. So the coefficients are 1, 5, 1, 5, 10, 10, 5, 1. Binomial expansion of power of 5. What do we need? We need the imaginary part. So what are the imaginary part? The imaginary parts are the one with I, this one, the other one here, and the last one here. So therefore, sine 5 theta is equals to the one with imaginary part, this one, 5 A raised to power 4. And what is our A? Return it back. Cos 4 theta B sine theta. The other imaginary part is this, 10A square IB. So minus 10 cos theta is A. That's cos square theta. B raised to power 3 sine cube theta. And the last imaginary part is this IB5. That's plus B sine theta raised to power 5. So that is how we get the expansion of sine raised to power sine 5 theta. So this is how we get the expansion of sine 5 theta, sine n theta. The previous one is cos raised to power n and sine raised to power n. The second one here is cos n theta and sine n theta. So sine 5 theta are the imaginary parts. What if I want to pick cos 5 theta? Cos 5 theta will now be the real part of it. The real part are the one without I, this one, the second one here, and this third one. So that is cos 5 theta. So but here we are going for sine 5 theta. So that is how we expand cos raised to power cos n theta and sine n theta using the Moivre's theorem. So the last application of this Moivre's theorem is the nth root of unity. Nth root of unity. So that is the last application of the Moivre's theorem. So application 3, nth root of unity is the nth root of unity. But before I talk about the nth root of unity, so let's briefly talk about a few properties of a trigonometric graph, sine and cosine. If I have y equals to sine x, for example, y equals to sine x, you know that if I start from 0, Sine 0 is 0. So the graph of sine x starts from origin like this, goes forth, come back, goes forth, come back, and not like that. Where this is 0, from here to here like this is pi, and from here to here is another pi, so making 2 pi. So this is another pi, that's 3 pi, to here, that's 4 pi. Now, from here to here is one complete cycle. From here to here like this is one complete cycle. And the time taken from here to here is the period. So this is t, one period. From here to here, so it's another complete cycle, another t, making 2t. So and not like that. So it tells us that the period of sine x is 2 pi. The period of sine x is 2 pi. So from here to here is 2 pi, from here to here is another 2 pi, making 4 pi. So we can say that the period of sine x is 2 pi. So, and if I want to express sine x in periodic form, so in periodic form, it will be y equals to sine x plus 2 pi. This is if I want to express one complete oscillation like this. So y equals to sine x plus 2 pi. Another complete oscillation, that's sine x plus 2 pi. And not like that. Because I have infinite number of oscillations, I will now generalize that if I have an infinite number of wave for sine wave, so y will now equals to sine x plus 2n pi, where n represent the number. Like this is first one, the second one, the third one, like that. So the same thing goes for cos x. If I have y equals to cos x, for example, so that one starts from here. The graph of cos x starts from 1. This is 1. This is minus 1. This is 1, 0. This is minus 1. Goes forth, come back, like that. Where from here to here is also pi. From here to here is 2 pi, 3 pi, 4 pi, and n pi. So we simply tell us that from here to here is one complete one cycle. So and the time from here to here is one period, capital T. So from here to here is another complete cycle, and the time from here to here is another t, making 2t. So which tell us that if I want to express cos x in periodic form, the period of cos x is also 2 pi, because from here to here is 2 pi. So if I want to express y equals to cos x in periodic form, it will be y equals to cos that x plus 2 pi. That is if I'm expressing a complete oscillation like this from here to here. So and we have many number of waves. So I'll just put 2n pi, where n represent the numbers of cycles. So what that thing tell me is that, so whenever I'm having, let's say I have cos 3 pi, for example, and I want to express this cos 3 pi in periodic form, since the period of cos is 2 pi, so it will just equals to y equals to cos that 3 pi plus 2 pi. So 2 pi represents one complete the time taken to complete one oscillation, 2 pi. So what do we want to use this thing for? So we know now. So the third application of the Moivre's theorem is nth root. Nth root of unity, or let's say nth root of complex number. Here now, or if z is equals to r into bracket cos theta plus I sin theta. So you observe that all the things that we've been using so far is either we use the Cartesian or rectangular form of complex number, or we use the polar form, or we use the exponential form. So we don't go beyond the 3 classification of complex number. So now, z raised power n, Okay, z is r cos theta plus I sin theta. If I express this cos theta and sin theta in their periodic form, you know, it will be equals to z equals to r into cos this theta plus 2 pi. This is one wave, because we have an infinite number of waves. I'll say 2n pi plus I sin theta plus 2n pi, right? So where n represent the counter, z1, z2, z3, z4. So n represent the counter. So this is z. If I now take z raised by 1 over n, for example, so z raised by 1 over n, it will be r raised by 1 over n into cos theta plus 2. Okay, let me use k. So let me use k. It doesn't really matter the letter I use to represent the counter. So I don't just want n. I don't want to be using n for both of them. So theta plus 2 pi k plus I sin theta plus 2 pi k. That one too will raise to the power of 1 over n. That one will also raise to the power of 1 over n. So, and according to the Moivre's theorem, whenever I'm having cos theta plus I sin theta raised to the power of anything, so that power will just multiply them. So, and here I have power 1 over n now. So this 1 over n will multiply all these angles. So z raised by 1 over n is equals to r raised by 1 over n into cos theta plus 2 pi k times 1 over n, like this. Because if I say everything here times 1 over n, so that n will be the denominator, plus I sin theta plus 2 pi k over n. That is it. So this is how we build the nth root of complex number. It means that whenever we are having a complex number, we first express them in polar form, and then we write whatever we have in polar form in periodic form by adding 2 pi k or 2k pi or whatever. Then we take the nth root. So where this k represents counter, k represents counter. Counter means from z0, from z1, z2, z3, z4. So k starts from 1, 2, 3, and all like that up to n that we are going. Now let's now apply this thing that we know. Let's apply it to solve a problem. For example, let's solve z raised by 3 minus 1 equals to 0. Okay, let's say we have minus I. Let's use z raised by 3 minus I equals to 0. Z raised by 3 minus I equals to 0. Z raised by 3 minus I equals to 0. So the first thing is that we collect like term. So collecting like term, we are going to have z raised by 3 is equals to, if I move this minus I to this side, I'm going to have z raised by 3 equals to I. Then I will now go and express this I in polar form. Don't forget, from the beginning we will express 1 plus 3i in polar form and whatever. So now let's express, we express this I, we then express I in polar form. Let's say I have z equals to I, for example. I will find the modulus and arguments. So modulus r is equals to, if I have z equals to I, let me just pretend I have I plus 0 to make it look like a complete complex number in rectangular form. So if I have z equals to I plus 0 now, r is equals to square root of 0 square plus the coefficient of I is 1. So I will have 1, right? And what is my argument? Argument theta equals to arctan of y over x. This is y, the coefficient of the imaginary part, y over 0. So 1 over 0 is infinity. If I take the tan inverse of infinity is 90 degree. And like I said earlier, I will not be using degree, I will be using radian. So 90 degree to radian is pi over 2. So tan inverse of 1 over 0 is pi over 2. I've gotten my modulus r and argument pi over 2. So if I now express this I now in polar form, don't forget this is where we are coming from. We are coming from z raised to power 3 equals to I. So I will express this I in r cos theta plus I sin theta, where my r is 1 and my theta is pi over 2. So we will then have, we are going to have z raised to power 3 equals to this I, if I express it in polar form, is 1, that is r into cos theta. My theta is pi over 2, cos pi over 2 plus I sin pi over 2, cos pi over 2 plus I sin pi over 2. The next thing is that we will now express the angle that we have here. Whatever angle that we have here, we express it in periodic form. You know from here now, after expressing z equals to cos theta plus I sin theta, we now express this cos theta in periodic form by adding 2k pi, because the period of sine and cosine is 2n pi. So I will now express this cos pi over 2 plus I sin pi over 2 in periodic form. So we are now going to have z raised to power 3. So since 1 is the coefficient, so it won't really matter. So let me ignore that one. We are going to have cos pi over 2 plus 2k pi. So 2k pi is the period. Then plus I sin pi over 2 plus 2k pi. Plus 2k pi. This is z raised to power what? 3. Now in order for me to find z, what am I going to do? I will now take the cube root of both sides. So take the cube root of both sides. If I take the cube root of both sides, this one will have, I'm going to have z. You know, cube root is like having raised power 1 over 3. So cube root of everything here is like having raised power 1 over 3. And you recall that whenever from here now, z raised power 1 over n, r raised power 1 over n, cos theta plus I sin theta, all raised power 1 over n. And if I have cos pi over 2 plus 2k pi plus I sin pi over 2 plus 2k pi, all raised power 1 over 3. And according to the Moivre's theorem, this power 1 over 3 will just multiply the angle that I put there. So we are going to have z equals to cos pi over 2 plus 2k pi all over 3, right? Plus I sin pi over 2 plus 2k pi all over 3. And that is all. We've built it up to this line. Then we now start find the value of z1, z2, z3. So this counter will now start operating now. Now this is z raised to power 3. How many solutions? So it will have 3 solutions. If it is z raised to power 4, it will have 4 solutions. So we now start with, when k is 0, that one will give us z1. So when is k is 0, if k is 0 here now, if I put 0 here, put 0 here. If I put 0 here, this side will not be there again. So we are going to have pi over 2 over 3. So if you press pi over 2 over 3, so we are going to have z equals to cos pi over 6, then plus I sin pi over 2 over 3, that's pi over 6, right? So you just press your calculator. What is cos pi over 6? We know that pi over 6 is 30 degrees. So cos pi over 6 plus I sin pi over 6, if I use my calculator, I'm going to have, so remember to change your calculator to radian. So cos pi over 6 is root 3 over 2. So this one will be root 3 over 2 plus I sin pi over 6 is 1 over 2. So I over 2, this is z1. So this is z1. Then when k equals to 1, so if k here now is now 1, you know we are going to have pi over 2 plus 2 pi here now, all over 3. So you press everything here. When k is 1, that one will now give us z2. So z2 will be cos, if you press pi over 2 plus 2 pi all over 3. So pi over 2 plus 2 pi all divided by 3. So this is 5 pi over 6. So everything here, if k is 1, no, we are going to have pi over 2 plus 2 pi. So this one will be cos 5 pi over 6. Then the same thing will happen to this part, plus I sine of 5 pi over 6. Then you press your calculator, you get Z2. So cos 5 pi over 6. So cos 5 pi over 6 is minus root 3 over 2. Sine 5 pi over 6 is 1 over 2. So I over 2. That is Z2. Then when k equals to 2, when k here is 2 now, that will give us Z3. So Z3. So if k is 2 now, you know we are going to have 2 times 2 pi. So that one will be 4 pi. So just press pi over 2 plus 4 pi divided by 3. So it is a pi over 2 plus 4 pi divided by 3. So 3 pi over 2. So everything here will be cos 3 pi over 2 plus I sine 3 pi over 2. And if I press cos 3 pi divided by 2, that's 0. Z3 equals to 0. Sine 3 pi divided by 2 minus 1. So 0 minus 1 is minus 1. So that's Z3. So this aspect is where most students find difficult to do. So Z3 is minus 1. Z2 is minus root 3 over 2 plus I over 2. Z1 is root 3 over 2 plus I over 2. So let's take one more examples and we conclude. Suppose we are given z raised to power 5 minus I minus root 3 equals to 0. Z raised to power 3 minus I minus root 3 equals to 0. Or z raised to power 5. So even before I will start solving, this one will have how many solutions? Z raised to power 5. It will have 5 solutions. So the first thing is to collect like term. So solution, this is the problem. We are asked to solve z raised to power 5 minus I minus root 3. So collect like term. Z raised to power 5 equals to, bring this one to this side, it will be root 3, and this one will be plus I. And the next thing is that the right hand side here, root 3 plus I, you express it in polar form. Root 3 plus I, you express this one in polar form. Where the modulus is square root of root 3 all squared plus I, the coefficient of I is 1 all squared. So that's 2. Root 3 squared is 3, 1 is 3 plus 1, 4. Square root of 1 is, square root of 4 is 2. And we find our argument. Argument is a tan inverse of y over x. Y part is 1 over root 3. So tan inverse of 1 over root 3, if you press calculator, your calculator must be in radian. So it's 30 degree. That's pi over 6. So after finding the modulus and argument, we express it in polar form. So we are going to have z raised to power 5 equals to, here now, my r is 2. 2 into cos pi over 6 plus I sine pi over 6. So after that, we take the periodic form of this pi over 6, pi over 6. What is the period of cos and sine? It's always 2k pi. So z raised to power 5 is equals to 2 into cos pi over 6 plus 2k pi, where k is the counter, plus I sine pi over 6 plus 2k pi. Okay? So now, z raised to power 5 now. We now take the fifth root of both sides. So if I take the fifth root of both sides, so take the fifth root of both sides. If I take the fifth root of this side, I will have z. So fifth root now, it means that everything here now raised to power 1 over 5. That's the meaning of fifth root. Everything here raised to power 1 over 5. Unlike the previous example that I have 1 here, so 1 doesn't really matter, so I ignored it. But here now I'm having 2, so I have to include it into all my solutions. So if I put fifth root here, and here now we'll share that fifth root, cos pi over 6 plus 2k pi plus I sine pi over 6 plus 2k pi, sorry, raised to power 1 over 5, right? So, and according to the Moivre's theorem, whenever we are having cos and sine with any power, so that power will just multiply cos theta and sine theta. So z equals to 2 raised power 1 over 5 into cos pi over 6 plus 2k pi all over what now? This is 1 over 5 times 1 over 5 plus I sine pi over 6 plus 2k pi all over 5. So, and then we start writing our solution. Don't forget that this k is the counter. So we now start setting that k to 0, to 1, to 2, to 3, to 4. When I set k to 0 now, when k equals to 0, that one will give us z1. So if k is 0 now, this part is 0. This part is 0. So we are going to have pi over 6 over 5. So if I press pi divided by 6 divided by 5, that's pi over 30. This 2 raised by 1 over 5 must be there. So this is 2 raised by 1 over 5 into cos pi over 30 plus I sine pi over 30. Then you press whatever cos pi over 30 gives. So it's 0.994. So Z1 equals to 2 raised by 1 over 5 into 0.994 sine pi divided by 30 is 0.104. You must put I, so that I makes it to be the imaginary part, plus 0.104 I. That is Z1. Then you do the same for Z2. Z2 is when K is 1. So now when K equals to 1, if K is 1 now, from here we are going to have 2 pi over 6 plus 2 pi all over 6. So pi over 6 plus 2 pi divided by 5. So 13 pi over 30. So our Z2, don't forget this 2 raised power 5 will be adding to it. 2 raised power 5 into bracket cos 13 pi over 30 plus I sine 13 pi over 30. So what is cos 13 pi over 30? You press that one. Then when K equals to 2, that will give us Z3. So when K equals to 2 now, put 2 here. This one will be 2 times 2 pi, that's 4 pi. So we are going to have pi over 6 plus 4 pi over 6 plus 4 pi divided by 5. That's 5 pi over 6. So that will be 2 raised by 1 over 5. 2 raised by 1 over 5 into cos 5 pi over 6 plus I sine 5 pi over 6. Then you press the numerical value of that cos 5 pi over 6. Then when K is 3, that will give us Z4. Where are we going? We are going to Z5. Okay. So when K equals to 3, that's 2 raised by 1 over 5 into, here now, K will now equals to 3. K will equals to 3. So if k is 3 here, 2 times 3 is 6 pi. So we are having pi over 6 plus 6 pi divided by 5. That's 37 pi over 30. So cos 37 pi over 30 plus I sine 37 pi over 30. Then the last one, when k equals to 4. So when k equals to 4, that one will give us Z5. So here now, if I put k to be 4, 2 times 4 is 8. So we are having, here we are going to have pi over 6 plus 8 pi divided by 5. 49 pi 2 raised by 1 over 5 into cos 49 pi over 30 plus I. So Z5 is equal to 2 raised by 1 over 5 into cos 49 pi over 30 plus I sine 49 pi over 30. Then whatever cos 49 pi over 30 is and sine 39 pi over 30, that's our Z5. So that is how to express, that is how to solve complex equation, end truth. So far we've talked about what is complex number. We said the complex number is any number in form of a plus ib, and then where that I comes from. So that I initially comes from square root of -1, and then we discussed about complex number can be in 3 form: the rectangular form, that z equals to x plus iy, and it can also be in polar form. So polar form is r cos theta and I sin theta form. Then we discuss how to find modulus and argument of complex number, and then the logarithm form of complex number. We move to the Moivre's theorem, so which is one of the integral part of this topic. So the Moivre's theorem has about 3 applications that we discuss: expansion of trig function and how to find the root